Okay, good afternoon and welcome. This is the third in our webinar series. Today's topic is potting and encapsulating compounds. I am the host and presenter, Michael Strong. And for today, we will have a webinar which is about 35 minutes in length, followed by a Q&A session. So you have in front of you a place where you can place your questions. These will be read out and answered at the end. And for now, I think people are starting to come in. So with that, let's get started. And welcome to the third installment of our webinar series. Today we're going to be talking about potting and encapsulating solutions. Now this is going to be a bit different than the And welcome to the third installment of our webinar series. Today we're going to be talking about potting and encapsulating solutions. Now this is going to be a bit different than the prior webinar series in that it has less of a focus on the individual products that we have, and it's more centered around the different chemistries, technologies that are available. When I started to prepare this webinar, I realized that there are simply too many options to go over that would make for a good webinar. So I think what we'll do is in subsequent webinars, we will go over the individual chemistries, and that will give me a smaller range of products that I can go over in more detail. Whereas here, my objective today is just to present to you the different types of solutions, distinguish them so that you understand how they apply to different applications, and then we can go into more specific product breakdowns in the subsequent webinar series. So with that, let's get started. So on the agenda today, what we're going to talk about is when to pot. In what circumstance do you distinguish when you need to conformally coat a circuit board versus when potting or encapsulation might be the more ideal solution? From there, we're going to look at the different potting resins that are available. Specifically, we'll break down epoxy versus silicone and polyurethane. And then the third one is a very encompassing sort of subset of this talk, understanding the specifications. And hopefully by the end of that, you'll be able to understand where the different chemistries line up in terms of how they're being used and what they can be applied, basically how they're specialized from one another. And then from there, we branch off into the MG chemical solutions. So I am going to present some of the different products that we have, but again, that topic I found was just too expansive to do in this webinar by itself, so more will come in subsequent webinars. And then the last section I want to focus on is choosing the right resin or chemistry to fit specific requirements. Okay, so situation one is when do you need to consider potting? So let's consider two situations. On the left, we have a circuit board, and on the right, we have the same circuit board. Now it is housed within an enclosure. Okay, so in option one, we can conformally coat the board, or option two, we choose to pot it or encapsulate it. So where do the two options line up? Well, an obvious choice here is that environmental stresses, both solutions are appropriate. Okay, and you can argue that potting and encapsulation provides enhanced protection against environmental stresses, and that more or less is true, but often people will opt to conformally coat either for ease of use or for weight considerations. And again, there is advantage to potting, but it's not that significant that it should sway you away from conformally coating. So that is a situation in which the two solutions more or less line up, and there's no clear advantage one versus the other. But what about in the instance of mechanical stresses? Here I've sort of exaggerated with the use of a hammer, and this is the main advantage that potting encapsulation provides over conformal coating, whereas potting provides you mechanical protection from things like sudden shocks and vibrations. With conformally coat, no, not so much. So that really is one of the main drivers distinguishing how you make that decision whether potting versus conformal coating is the right way to go. All right, so let's look at the different potting resins. And again, we're just going to look at the more traditional potting resins. It's by no means exhaustive, but this across most competitors are the chemistries that are most often used. Option one, we look at epoxy resins. And epoxies just inherently draw up images of very tough, durable materials. They're very rugged. They're very easy to use. And welcome to the third installment of our webinar series. Today we're going to be talking about potting and encapsulating solutions. Now this is going to be a bit different than the prior webinar series in that it has less of a focus on the individual products that we have, and it's more centered around the different chemistries, technologies that are available. When I started to prepare this webinar, I realized that there are simply too many options to go over that would make for a good webinar. So I think what we'll do is in subsequent webinars, we will go over the individual chemistries, and that will give me a smaller range of products that I can go over in more detail. Whereas here, my objective today is just to present to you the different types of solutions, distinguish them so that you understand how they apply to different applications, and then we can go into more specific product breakdowns in the subsequent webinar series. So with that, let's get started. So on the agenda today, what we're going to talk about is when to pot. In what circumstance do you distinguish when you need to conformally coat a circuit board versus when potting or encapsulation might be the more ideal solution? From there, we're going to look at the different potting resins that are available. Specifically, we'll break down epoxy versus silicone and polyurethane. And then the third one is a very encompassing sort of subset of this talk, understanding the specifications. And hopefully by the end of that, you'll be able to understand where the different chemistries line up in terms of how they're being used and what they can be applied, basically how they're specialized from one another. And then from there, we branch off into the MG chemical solutions. So I am going to present some of the different products that we have, but again, that topic I found was just too expansive to do in this webinar by itself, so more will come in subsequent webinars. And then the last section I want to focus on is choosing the right resin or chemistry to fit specific requirements. Okay, so situation one is when do you need to consider potting? So let's consider two situations. On the left, we have a circuit board, and on the right, we have the same circuit board. Now it is housed within an enclosure. Okay, so in option one, we can conformally coat the board, or option two, we choose to pot it or encapsulate it. So where do the two options line up? Well, an obvious choice here is that environmental stresses, both solutions are appropriate. Okay, and you can argue that potting and encapsulation provides enhanced protection against environmental stresses, and that more or less is true, but often people will opt to conformally coat either for ease of use or for weight considerations. And again, there is advantage to potting, but it's not that significant that it would sway you away from conformally coating. So that is a situation in which the two solutions more or less line up, and there's no clear advantage one versus the other. But what about in the instance of mechanical stresses? Here I've sort of exaggerated with the use of a hammer, and this is the main advantage that potting encapsulation provides over conformal coating, whereas potting provides you mechanical protection from things like sudden shocks and vibrations. With conformally coat, no, not so much. So that really is one of the main drivers distinguishing how you make that decision whether potting versus conformal coating is the right way to go. All right, so let's look at the different potting resins. And again, we're just going to look at the more traditional potting resins. It's by no means exhaustive, but this across most competitors are the chemistries that are most often used. Option 1, we look at epoxy resins. And epoxies just inherently draw up images of very tough, durable materials. They're very rugged. They're very easy to use. So one of the things that make these materials stand out is they're known for their adhesion just to a wide variety of substrates and just that enhanced chemical resistance that you get over more other options available. Now, the one thing you want to consider though, if choosing an epoxy, is that these materials are typically, they cure to a very hard, rigid finish. Now, that's not always true, but for the most part, people will choose epoxy based on their sort of very tough, rigid finish. And that may not necessarily work if you have delicate surface mounted devices, and we'll look more into that later. Polyurethanes are also popular materials, and one of the distinguishing features of these is that they can be fine-tuned with respect to both their cure and their hardness. So these materials can be made as hard as a construction hard hat, or they can be formulated to be as soft as a marshmallow. So it really gives you that kind of latitude in terms of different hardnesses based on what you may need. And also the cure time can be fine-tuned. Some of them can be almost a snap cure mechanism, whereas others can have an open, long pot life, which may be ideal in certain circumstances if you have a high volume demand. One of the things though that kicks out polyurethanes over other chemistries is the upper temperature limit. So typically about 120, 125 is about the tops that these materials can go before they start to thermally degrade. So that's typically what rules out polyurethanes for a lot of applications. And then finally, we look at silicone. And silicone has two very distinct advantages over other chemistries. And one is the wide operating temperature. So typically you're looking at between about -60 to 200 degrees Celsius. But some of the more extreme ones can place them between about -120 and up to 320 Celsius. So that's just an advantage that really other chemistries don't have. And the other advantage is their low modulus, which is basically a way of saying they don't physically stress components because they're so soft. They don't exert a lot of stress on these. So very ideal if you're dealing with very delicate components, kind of the opposite of what you have with epoxy. But again, some of the considerations or drawbacks are adhesion can be an issue. As well, you don't have the level of chemical resistance that you do with the other chemistries. All right, now let's look at some of the specifications that we will typically list in the technical data sheet. So understanding these will really help drive customer decisions in terms of what product may meet their specific requirements. All right, so we're going to break this down into three main sections, which typically dictate whether a material is suitable or not. That's thermal data, mechanical data, and then finally electrical data. So starting with the thermal data, what are some of the things that we typically list that may be a bit obscure for the average consumer? Well, two things come to mind. The first is the TG, or the glass transition temperature. So what this value signifies is that it's a temperature, and usually it's more aptly described as a temperature range, but it's a temperature at which beyond that, the polymer system starts to soften. So you basically transition from what's called a ridgy or glassy state to more of a rubbery, softer state. And then complementary to that is the CTE, or the coefficient of thermal expansion. And this actually very much feeds off of the TG. So the CTE is a measure of how much a material will expand for every degree that you raise the temperature relative to its initial size. So here's what I'm talking about. Let's say we place a probe on top of a cylindrical sample, and then we tell that probe, okay, exert a very constant force. So the force that the probe would be exerting, pushing down on that sample, does not change. It stays the same. Then we put it into a thermal chamber, and what do we see? Well, as we continue to heat the sample, what we notice is that it starts to soften. So what the machine will record is that displacement of the probe from the starting position. And since we haven't added any additional force, the only thing that's changing is the material's ability to resist that probe. So as it softens, it exerts less force in terms of how it's able to resist. And you see that in terms of the slopes, and we're going to see that now. So you see the section labeled CTE1. This is how much the material expands with every degree of temperature rise before the glass transition. Okay, so what do we conclude? Because the slope of this line is more flat, the material is harder. It's not expanding at the same rate for relative to how much you increase the temperature. Then this sort of flat part here is where we call the glass transition. And again, you see it's not a very distinctly sharp temperature. So basically we do a lot of manipulation to try and extrapolate a specific glass transition. But then you see beyond that, as that slope becomes more vertical, that signifies that that material has become less, or softer, I should say. So that sort of should help conceptualize both the concept of glass transition and the coefficient of thermal expansion. Now, mechanical data is something that you can take into account in terms of how well a material will respond to a specific stress. And we know that from a lot of our customers, based on their applications, that these materials would be put under a lot of stress. So we need to make sure that these materials are able to handle it and still perform. So these are the kind of tests that can help us understand that. So the first one I want to draw your attention to is the tensile strength and percent elongation. So with this test, we make a specimen that is sort of nicknamed a dog bone. And you see it's a very thin section in the center there with two ends. And what we do is we place those ends in vice grips, okay, and secure it very firmly. Now, once it's secured, basically what we do is we put it in a machine that's going to try and tear that sample apart. So we hit play, and these vice grips start to pull in opposite directions, and eventually the material will expand and start to give. So with this, we've determined two values here. First is the tensile strength, and the tensile strength is that material's ability to prevent being deformed, or how much it resists being pulled apart. The percent elongation is, if we look at that thin section where it broke, how much did that expand relative to its initial size before it did tear? So let's, for example, say that that thin section is 1 inch long. We perform the test, and by the time we finish, we note that it had stretched to 2 inches long at the point at which it broke. So the percent elongation in that example is 100%. It doubled its size before it, in fact, did tear. Next, let's look at the compressive strength. And compressive strength is actually sort of the opposite of the tensile strength, whereas the tensile, we try to pull something apart. In a compressive strength, basically what we do is we try and understand how well a material resists being crushed. So with that, what we do is we make a cylindrical block and we place it between two cylinders. We hit play, and it continues to move in on the sample until basically the sample yields. It's crushed to the point where it no longer really offers much resistance to the cylinders, and then the test shuts off. So this would be useful in determining, say, if the sample was to be under an immense amount of pressure, will it be able to withstand that pressure, or is it sufficient to potentially crush the material? So that's sort of where this test sort of aligns in terms of understanding where it might work in certain situations. And then finally, let's look at the lap shear testing. And this is a test that looks at the relative adhesion of a material for different types of substrates. So basically what we do is we make a lap shear. We overlap two substrates and they're held together in a thin section by the material itself. And what you do is you place the ends of each side in vice grips, secure it very firmly, and it works very much at this point like the tensile strength test. You hit play and you pull them in opposite directions until in fact the two coupons pull apart, in which case the adhesive strength of the material has failed. So that's noted as the lap shear test. And you can do it in not only different substrates, but different combinations of substrates, which is applicable to a lot of people if they want to know if a particular material is going to adhere to a type of substrate or if they would need to pre-treat it. Then lap shear testing is a good way to understand if that's true or not. And then finally, we measure the electrical data. Now, truth be told, for potting materials, yes, we measure it, but I don't often find that it has much influence in making a final decision. And typically what people want to know is whether a potting compound can withstand a certain voltage. So with that, what we do is we run what's called a breakdown test. And a breakdown test is basically where you make a tiny disc and you slip it in between two electrodes. Okay, so the only thing that's preventing a short is the fact that your sample is insulative. It's preventing the two contacts from shorting each other out. So once you do this, you simply ramp up the voltage until the static charge is enough on the surface to cause a breakdown through the sample, and then again it shorts, it grounds, and the test stops. So one thing you have to notice is that the sample thickness will determine and have an influence. So what we do in that situation is we try and standardize it to a given thickness, and I think we do it to about 3/8 of an inch or something. And that's a way just to standardize it so that you understand and can compare materials in a better way, rather than just if it was a testing bias and in one situation the test sample was made thicker than the other. Typically we get between about 40 and 50 kilovolt breakdown for these specimens. So people may want to know, okay, if I potted an inch thick, do you think it would be able to stand 500,000 volts or something like that? So that's typically the only question we ever get in terms of the electrical data. And so this is the test that we run to try and help with that. Okay, so now let's segue into some of the different solutions that MG Chemicals offers. All right, so we start with our flagship potting series, the Epoxy 832 series. So this series comprises 7 different products, with the common denominator being that they are not flame retardant, meaning if you set them on fire, they will continue to burn. They will not self-extinguish. That doesn't mean that they're not distinguished in other ways, but that is the one thing common in the 832 series that distinguishes it from the other series that we're going to look at next, and that these products are not flame retardant. So flame retardancy is not a requirement. We should consider the 832 series. So within that, we have low viscosity general purpose. And again, if people don't describe any kind of exotic requirement, then typically we can get away with recommending materials like the 832 HD, the 832B, which is pictured on the bottom right there. That's a general purpose 2-part black epoxy resin, or the 832C, which is like the 832B, only it doesn't have the black colorant, so it's got that sort of amber clarity to it. We also have the 832WC, and this is a water clear two-part epoxy. So again, that has the same advantage of the 832C, only it has more clarity, and that typically comes into play when you're dealing with someone looking for better aesthetic. The 832FX is a semi-rigid, flexible epoxy, so it does have a lower modulus than the harder materials, and that could be advantageous either with aggressive thermal cycling or in situations where, again, there's delicate components and people are worried about sudden expansion contraction. So these materials being a little bit less stressful may be more ideal. And then finally, we have a high temperature epoxy that can handle temperatures over 200 degrees, which isn't typical. Typically, you're looking at about 140, 150 degrees Celsius for most epoxies, whereas the HT can handle comfortably about 225 degrees. So again, just a table to highlight some of the main properties that we talked about before. Hardness is just a measure of how hard a material is. It measures how difficult a probe is to sort of penetrate. And I highlight there the 832FX, 88A meaning it's much softer than your traditional epoxy, which again usually ranges in the Shore D 80 range, which is, you know, sort of equivalent to, think about a hard hat that they wear in construction. And then that's also reflected in the value below, the percent elongation. So this is a flexible material, meaning it can stretch a lot higher and it has a lower glass transition. The other thing that I want to draw your attention to is the 832TC. TC meaning thermally conductive. So these materials are better at moving heat, which can be important if you have something that generates a lot of heat. You want a material to encapsulate it that draws heat away from that. So the thermally conductive material does that quite well. And the last thing I want to mention is right on the end there, 9500. Now that is not a two-part epoxy. That's a general purpose, but it is a one-part epoxy. So its main advantage is convenience. Okay, with this material, you don't have to measure out the ingredients. You don't have to mix it. That's already done for you. You simply dispense it and cure it. So the one thing I want to caution is that with one-part epoxies, they are not room temperature curing. So this particular material must be cured at elevated temperatures. It does not cure at room temperature. So if that is something that it cannot be accommodated, we cannot consider the 9500. The other thing that distinguishes the 9500 is it seems to have enhanced chemical resistance when we compare it to our other epoxies. So that could be a consideration if somebody has a very aggressive environment and this type of material might be of use. Next, we look at the 834 series, and unlike the 832, the 834 are flame retardant. So if we take a strip of a more traditional unfilled material and apply a flame to it, eventually what's going to happen is it's going to set on fire. And even if we were to remove that flame, that fire would continue to propagate and the material would not self-extinguish. Whereas with the flame retardant materials, what we see is once we apply a flame, once we remove it, the material tends to form a lot of smoke, tends to char easily, and so with that it's able to self-extinguish and not propagate. Now within this series we have two materials that meet the V0 standard, meaning we've tested it internally and found that it was compliant to the standard, and then we do have one that is listed. So these are flame retardant and thermally conductive. The thermally conductive, that's just because of the nature of the filler that we have to add in order to get flame retardancy, but because of that they are higher viscosity, and so they're not quite as good in terms of leveling out and wetting out very intricate geometries. So within that we have the 834B, which is a generic two-part epoxy. Again, good thermal conductivity, and this one meets the UL 94 V0 standard. We've tested it internally to meet it, but it is not certified by UL. The same goes for the 834FX. This one is a softer, flexible material though. So again, very ideal if you have aggressive thermal cycling or delicate components. You may want to consider the 834FX if flame retardancy or thermal conductivity is needed. And then finally we have the 834 HTC, and this is certified as meeting the UL 94 V0 standard. Good conductivity as well at about 1 watt per meter Kelvin. Next we look at polyurethanes, and again, as I mentioned in the slides before, these are versatile materials in terms of variable hardness and cure rate. So this is a fairly new line for us. We have 3 basically general purpose potting compounds. So we look at the 8800. The 8800 is a fast setting semi-flexible polyurethane. So again, it has lower hardness than materials that you're more used to, lower glass transition, and a very short work time. So a lot of people like that for that feature. Very low viscosity as well. Whereas the 8810, kind of the opposite of that, in that it cures to more of a solid plastic and has a 45-minute working time. And then finally, the 8820 is a high temperature polyurethane. So we highlight its max temperature at about 150, which again is quite a bit higher than you get with traditional polyurethane, so kind of known for that. The one consideration I want to make everyone aware of, though, is that these materials are much more prone to moisture contamination than are silicones or epoxy. So what happens is if you have moisture ingression into the resin, they react to form CO2 as one of the byproducts, and these will cause very unsightly large bubbles in the cured product and even within the bulk of the material, which could be very problematic if you have an air pocket. It may not be providing the protection that's required. So these are formulated to account for that, but it's just that the user has to know how to properly use polyurethanes, how to properly store these materials, whereas the other ones, it's not so much of a consideration. And then finally we come to silicones, and as I mentioned before, the main advantages here are the wide operating temperature range. Again, we go up to 200 degrees Celsius and above, and this idea of low modulus, which is basically a way of saying they don't stress mechanically the components as much because it's a softer material. So we have more general purpose, and again, I just sort of highlighted something that's a stretchy material. So RTV615, and that's an optically clear 2-part silicone, whereas the 627, 630 are more general purpose, and one's gray and one is blue. We also have high temperature options available. So high temperature means that continuously you can use them to about 260 degrees Celsius, but you could jog up to about 320 degrees for a max. And they say intermittent, which usually means 15, 30 minutes cycles. You can go up to these kind of temperatures. So that's the RTV116, 560, and 566. So these are red compounds. They incorporate red phosphorus to give it that high temperature resistance. And then finally, thermally conductive materials. These are materials that are able to dissipate heat. So if you have something that generates a lot of heat, these may be a more ideal material for you. The TIA 208R, 216G, or 222G. And again, I'm going to, in the future, do a webinar that focuses more on the specific products. So I know I'm going a bit fast here, but we're going to go and do a deeper dive into these chemistries in a subsequent webinar. So that brings us to our last topic, choosing the right resin. So normally I reserve this part for choosing the right products, but here, since we've focused more on just the chemistries, I'm going to go over some criteria in terms of how you choose the right resin system. All right, so to do that, we're going to look at 4 main considerations. The first being the temperature, and next we're going to look at the chemical resistance, mechanical protection, and then finally IP or intellectual property protection. So start with temperature, and that's just a great way to rule out certain chemistries or favor other ones. It's very black and white or obvious. So you have urethanes. In terms of their upper operating temperature, they're typically good to about 120 degrees Celsius. So if your customer says, well, it's going to be operating at something above 120, we can rule that out. Epoxy, again, typically about 150, but the high temperature can handle up to over 200 degrees Celsius. So there are exceptions, of course. And then silicone is the most versatile. Pretty much all of them operate up to about 200, with some going as high as 260 with brief jogs up to about 320 degrees. So temperature is a great one. In terms of the lower temperature resistance, they don't differ that much. With silicones, you're looking at usually about -60. Urethanes and epoxies about -50. So it's not a huge difference. It's not necessarily as useful as the upper operating temperature, but it's something to consider. Now, chemical resistance is something that distinguishes, again, the three different chemistries, but you have to be careful in making these broad statements because even within epoxies themselves, there's a wide latitude of degree of chemical resistance. So I say this more in terms of generalities, but more or less it does hold true. And things we need to know is, okay, what specific chemical would the compound be exposed to? Because if it's something that all three chemistries would be able to hold up to, then the improved chemical resistance really isn't or shouldn't be a factor in our decision because it's somewhat null based on every chemistry meeting the certain threshold. The other thing we want to consider is the degree of exposure. Is it partial? Is it outside where, yeah, it might be exposed to it, but it dilutes very quickly. So in the long run, it's really not all that exposed versus being fully submersed in a fluid, say under the hood of a car or something. So then let's basically do this and summarize how do these different chemistries distinguish themselves. So let's take silicone, for example, and let's say we have a standard solvent. We'll say it's acetone. We immerse it in the solvent and we see a certain degree of fading based on the exposure. Now let's compare it to a polyurethane. Again, the same chemistry, an acetone, and it will fade somewhat, but in general, it's going to hold up better than will the silicone. That's not universally true, but for the most part, it's true. And then again, for the epoxy, we hit it with the solvent, and what we find is that generally epoxies outperform the two chemistries. So again, everything's sort of stacked relative to one another, and it's not absolute. There are exceptions, but more or less, if someone says, I need extreme chemical resistance, we're going to consider epoxy first off. Okay, so mechanical protection, again, we're looking at if that's a factor, will this material need to be protected from shocks, jolts, things like that. So how do we classify the different chemistries? Well, if we start with epoxies, again, epoxies are typically very hard materials. So they are the best in terms of deflecting and absorbing shocks, vibrations, that sort of thing. They provide the best mechanical protection. But again, since they are so hard and rigid, they do have a tendency to crack, whereas softer materials won't do that. Polyurethane, again, they're very versatile, so you could have either or. You could have a material that's very hard, or you could have one that has a much lower modulus, much softer material, so that rather than absorb it, it may, deflect it somewhat, but you would have more compression in this example. And then finally, we go to silicone. Silicone, known as a softer material. So what typically happens is it squishes the easiest. It would, undergo these sort of elastic deformations and provide the least amount of protection for the potted material. And then finally, IP protection, which comes up sometimes, and that has more to do with the color of the potting compound more than the actual chemistry itself. Although again, you have to consider, if you wanted to and you had the time and you were crafty, you could probably cut out mechanically a silicone and remove it with a box cutter, whereas, epoxies, because they have such strong adhesion, that is just substantially harder to do. And the reality is you'd probably wreck the circuit board before you cleanly remove the epoxy. So it's very good for IP protection. But some people, they may want their technology protected, so they pot it so that their competitors aren't able to see what they're doing. In other situations, what they want is something that is translucent or see-through. And they want this in order to monitor something, whether it's a sensor or something like that. They want to make sure that they can see it to make sure it's still working. Or they would want a material that, again, is completely opaque so that no one can see what's underneath and their technology cannot be stolen. All right, so what are the conclusions that we can draw from today? Well, the first thing is that potting provides not only enhanced protection from the environment when compared to coatings, but also physical protection against shocks and disturbances. Traditionally, we use resin such as polyurethane, which again has a tailored curing and hardness, epoxies with a premium adhesion and protection, or silicone, which has a wide operating temperature. Specifications such as the TG or glass transition, coefficient of thermal expansion, tensile strength, lap shear strength, and electrical breakdown help users understand the limitations of the materials. So with that kind of information, they can understand maybe better how the materials compare to one another and whether a material is right for their application. MG Chemicals has several solutions available, such as the 834 and 832 and 834 epoxy series, polyurethanes, and many silicones. And again, I'm probably going to go and do a deeper dive into the individual chemistries here so that it can help you gain a better understanding of the specific MG Chemical solutions, their limitations, their strengths, that sort of thing. I didn't do that too much today just because I didn't feel like there was enough time to do that in depth, so that'll come out in future webinars. And then finally, selecting the correct resin depends on requirements. And for here, we can look at different things like the operating temperature, solvent exposure, the need for mechanical protection, or in some cases, the color, whether it's inspection, we'd use a transparent, or if it's IP protection, we want something more opaque that can't be seen and helps protect the intellectual property. Okay, I want to thank you for your attention. Again, you can contact me at my primary email listed above or at the support account, which I monitor, and if needed, you can call me direct. So we'll now open the floor to questions. Thank you for your attention. Okay, so that wraps things up. We apologize for the technical difficulties we experienced and thank you for your patience staying on with us. So now if there are any questions, I'd be happy to answer them at this point. Okay, so we just see one. So I'm going to go ahead and answer. If you have another question, feel free to post it, or you can just email me any questions you have and I'll respond to you directly. So the one question that came in is potting and encapsulation interchangeable terms? And the answer is no. So with potting, what we're talking about essentially is almost like burying a circuit board under a lot of material. And so these are PCBs that are in cavities or housing, and you essentially fill that housing. So you completely bury it. And this gives you added protection as well. It gives you added insulation. Whereas encapsulation, the objective is simply to completely cover the components that you're trying to protect. So it's more or less a matter of thickness. That's the main consideration. Okay, next question. What would you suggest for a customer looking for a high voltage epoxy? We don't necessarily have epoxies that distinguish themselves based on insulation. So typically when we measure these, they come out to around, the range is about 10 to the 14, 10 to the 15 ohm centimeters in terms of bulk resistivity. So, there's not much that distinguishes. And to be quite honest, for a lot of people, they are dealing with voltages that a half inch to an inch of potting compound can easily handle. So someone called me today and I recommended they consider potting a copper coil, and they're saying, well, they're the coils are spaced 2 millimeters apart, and they would go through voltage surges of about 4 to 5,000 volts. Well, I mean that's easily accommodated by pretty much all of our epoxies. So yeah, there is some difference to them, and you can sit down and sort of calculate something. But generally, what we come to recommend is if all they're looking for is a high voltage, then we'll recommend something that's more general purpose, like the 8810 polyurethane or the 832B, 832HD epoxy potting compounds, and they're just easy to use. They have low viscosity, so they wet out and flow very nicely. But again, there's nothing necessarily specified for high voltage, and you can sort of adjust the amount of protection you'll get simply by adding more material. So it's not very often that we find something that's outside of the capabilities of what we currently have. How sensitive are mixed ratios with respect to volume and weight? So when you're dealing with epoxy, there is a little bit of forgiveness, and the typical rule of thumb is you can be off by, in the area of say 2 to 3% with the mixed ratio, either by volume or weight. It really doesn't matter. And the material will still cure. Now the hardness will be the most effective property and the most obvious, but your properties in terms of how they're affected, tough to say, right? Because we measure things in terms of ideal stoichiometry, meaning they are mixed in the proper ratio. With polyurethanes, though, it's a bit different. So if you have too much of the resin or part A component, then essentially you're going to get a cured compound that is softer. Whereas if you add too much part B, well, the excess part B will actually react, and that is that side reaction that I talked about. It reacts with moisture, so it will react with the atmospheric moisture, and that forms sort of a separate compound altogether. And what you typically end up with is you get a harder cured product. And again, the final cured properties, tough to say how it'll actually sort of come out. I mean, it depends on the deviation, of course, as well. But I would say that polyurethanes are actually a bit more forgiving. The only thing you can do with polyurethanes to inhibit cure is if you add too much of the part A resin. If you add too much part B, that excess actually will react on its own. But again, you'll end up with a harder compound. Okay, moving on. Do all potting compounds offer substantial weatherproofing? Or sorry, waterproofing? And yes, of course, because again, you're completely covering it and sealing it off. But what I caution people is that if this was to go directly underwater for permanent exposure, then really this has to be a secondary protection. And then typically people will hermetically seal the PCB and then they'll pot it. So the hermetic seal in the housing provides sort of the primary waterproofing. And then in case that somehow becomes compromised, then the potting is more of a secondary. I would say no, it's probably not going to completely seal and waterproof anything if it's just completely immersed. Okay. Is there anything that can help to avoid manual mixing? Yeah, there's a couple things you can do depending on your volume. So we do have some of the lower viscosity products that are available in manual mix cartridges. So in that situation, they are packed in the proper mix ratio, and you can simply attach a mixing nozzle. And the nozzle has helix that sort of wind in opposite directions. So this kind of mechanical force combined with the pressure of pushing it through the nozzle is what mixes the two components. So then you simply dispense and you have a mixed material. The other option, if you're moving into higher volumes, is called meter mixing. And that's basically the same concept, only you're dealing with perhaps holding tanks. So you can mix much larger volumes for that. So that helps not only speed up and automate the process, but it's also an airless mix system. So you don't have to worry about air being ingressed into the system, which happens if you manually do it. So those options are available. Okay, do you have recommendations or relationship for application equipment for customers that are setting up a potting process? So that question actually leads in nicely from the prior question. And the answer is yes. We have worked with some companies that sort of specialize in this kind of equipment. So PVA is a company that we've worked with, SCS, as well as Nordson Asymtech. So there are companies that work on these solutions, and they can actually tailor it based on not only your volume, but also the consistency of the material, whether it has filler or not, that sort of thing. So they're very knowledgeable in different kinds of products and dispensing. So short answer is yes, and you can contact us directly if you have someone in mind. Okay, so that is all the questions that I see for now. And unless there's something else, I think we'll wrap things up. So if you have any other questions, feel free to email me, and we will see you next time.